Let's cut right to the chase and uncover the truth hiding behind mobile processor performance. If you follow consumer hardware at all, you already know that spec sheets, yeah, they really only tell half the story. So today, we're cutting through all the marketing hype to decode the exact structural and numerical breakthroughs of the Samsung Exynos 2700. We're going to dive deep into the actual internal data to see exactly how much it's improved over the last generation, and more importantly, how it stacks up against Qualcomm's next-gen chip. We've got a lot of ground to cover today. We'll start by busting the benchmark illusion, look at how past limits were overcome, dive into the crucial 2.5-watt sweet spot, check out how it actually outperforms the competition, explore AI and the memory wall, and finally unpack the massive strategic leverage this chip provides. All right, kicking things off with part 1, the benchmark illusion. So judging a mobile chip strictly by its peak laboratory scores, it's honestly just ignoring the physical reality of a smartphone. Think about it. Your phone doesn't have loud, spinning cooling fans like a gaming PC, right? You literally can't carry a desk fan in your pocket. When manufacturers design processors assuming unlimited power and cooling, they're selling a lab fantasy. In the real world, performance is entirely dictated by strict thermal boundaries and pure power efficiency inside a tiny enclosed space. And this illustrates perfectly what happens when a processor pushes past those physical boundaries. When a chip runs too fast and draws too much power, it generates a massive amount of heat. And because there's nowhere for that heat to go, the system is forced to step in. It intentionally throttles your user experience just to protect the hardware. You know when you're gaming and your frame rate suddenly drops, the screen dims, or the UI starts lagging? Yeah, that's exactly what's happening. A chip that sprints so fast it collapses from its own heat is basically useless for any sustained workload. Moving on to part 2, let's talk about how the 2700 actually overcomes these past limitations. In the past, the Exynos 2600 tried to fix this structurally, using heat pass blocks to lower internal resistance. But physical cooling alone, it has hard limits. Just look at this 10-minute stress test data from Asphalt Legends. The 2600 suffered severe performance decay. I mean, it started out strong at an impressive 113 frames per second, but then critical thermal throttling kicked in, dragging it all the way down to 80 FPS. That is a massive 30% drop in frame rate in just 10 minutes. It completely proves that if the chip itself is inefficient, making the heat pipe bigger doesn't really solve the problem. Now, this is where it gets really incredible. The 2700 solves this physically at the silicon level. By integrating Samsung Foundry's second-generation 2nm SF2P process, it fundamentally reduces the chip's baseline power consumption. So instead of desperately trying to cool down an inefficient chip, it just stops the heat from generating in the first place. This isn't a minor tweak, it's a massive generational leap. It completely transforms a system that used to suffer from overheating into one that is remarkably sustainable and stable. Let's look at part 3, the 2.5 watts sweet spot. To truly measure this new efficiency, we first have to establish the only boundary that actually matters in a smartphone, and that is the 2.5 watt limit. In a mobile device, you only get about 2.5 watts of continuous power before you hit thermal limits or completely drain the battery. So true dominance isn't about just brute forcing power through a bigger pipe. It's about how much more computational work you can pull off inside that exact same 2.5 watt energy budget as your competitors. Which brings us nicely to part 4, how it actually outperforms the competition. This is the ultimate scorecard showing not just generational improvement, but the massive gap with the competition. When we test both the Exynos 2700 and Qualcomm's next-gen chip under that strict real-world 2.5 watt budget, the 2700 absolutely crushes the Qualcomm baseline. We're talking a massive 19% advantage in multi-core CPU processing, which directly translates to how fast heavy apps launch. And even more impressively, exactly at that 2.5 watt limit, GPU output is 22 to 24% higher. It completely nails the sustained frame rates in high-end games that the previous generation struggled so hard with. If we look at this data curve, you can clearly see where the SF2P architecture pulls ahead. Sure, if you pump unlimited power into both chips, the competitor might edge out the absolute peak, but that's totally unrealistic for a phone. Look at the shaded middle area instead. That is the mobile sweet spot. Under strict power limits, the Exynos 2700 delivers significantly higher performance without needing excessive voltage. And this middle zone, that's where your actual everyday mobile performance happens. When we translate this architectural superiority into physical battery endurance, the difference is undeniable. In everyday use, the competitor's Pro model draws about 185 milliamps. The Exynos 2700, just 161 milliamps. That is a 13% drop in baseline power consumption. And that's not just a cool number on a chart, it means a tangible, real-world extension to your battery life. Plus, because the chip naturally runs so much cooler, it delays that dreaded thermal throttling even longer.
All right, moving right along to part 5, AI and the memory wall.
Beyond standard graphics and CPU crunching, we really need to redefine how we measure artificial intelligence on mobile devices, because the old metrics, they just don't work anymore. Competitors usually rate AI based purely on the NPU's clock speed, but that is fundamentally flawed. The Exynos 2700 strategy targets something completely different: memory bandwidth. They figured out early on that on-device AI generation isn't just bottlenecked by processing power, but by how fast you can move the data. The real limit of AI isn't just computing speed, it's data transfer speed. This difference becomes crystal clear when running massive large language models right on the device. When you run a colossal 3.18 billion parameter LLM locally, the Exynos has about a 5% lead over the competitor in simple compute reading speed. But the actual game changer is during the token generation phase. Because the Exynos 2700 physically widened the data bottleneck, it secures a massive 18% speed advantage when the AI is actually writing and generating text. Think of it like a master chef in a kitchen. The NPU is an incredibly fast chef. But if the hallway to fetch ingredients is too narrow, even the fastest chef has to stand around waiting. By fundamentally widening this memory bandwidth highway, the Exynos ensures the data pipeline never clogs up. The NPU never spends a single second idling. And that right there is the secret sauce behind that 18% advantage in AI generation speed. Finally, let's wrap up with part 6, the strategic leverage. Okay, so we've seen the data, the thermal issues are fixed, the 2.5-watt power efficiency destroys the competition, and the wide memory bandwidth gives it a massive edge in AI. Now let's step back. Why do these specific engineering wins matter so much to the broader consumer hardware market? Reaching performance parity at 2.5 watts isn't just about corporate pride. It is a massive financial lever. Samsung's mobile division spends over 13.8 trillion won every single year buying external chips. That's more than 10 billion US dollars. Having an efficient in-house chip reclaims a huge chunk of that external spending. And that capital, it gets reinvested right back into the devices you buy, funding better camera sensors, nicer displays, and bigger batteries. This is literally the ultimate bargaining chip in the supply chain. By proving equal or better power efficiency, this technologically superior in-house chip acts as a ruthless suppressor for BOM, or bill of materials costs. It sets a hard price ceiling that forces external vendors to compete on price. This immediately generates massive return on investment and directly protects the operating margins of next-generation flagship smartphones. So they've completely cured the thermal decay that plagued the 2600, officially ended the narrative of the competitor's superiority with the SF2P process, and absolutely dominated Qualcomm at the 2.5-watt mobile limit. Samsung isn't just offering a backup plan anymore, they are aggressively claiming hardware leadership. So the big question is, how far will this overwhelming technological independence push the limits of our next-generation smartphones? Thanks for tuning in to this explainer, and keep looking beyond the spec sheet.